So welcome everybody. Today I'm very happy to introduce Annie. She did her PhD at Trinity College in Dublin, and nowadays she's a postdoc at Niels Bohr Institute. She works with many aspects of quantum field theory, and today the title of her talk is Quantum Chaos and Integrability in Super Young Mills Theory. Thanks a lot for accepting our invitation, and please, and the words is yours.
Thank you. So let me just start quickly sharing my slides. Okay. Okay. Yeah, so let me thank you for inviting me to talk in the seminar series. And so, let me actually also hide all this stuff here on my tablet. Okay. So in this talk, I will discuss work done together with Tristan McLaughlin and Raul Pereira. And it is mainly based on these two papers here, where we look at chaos and integrability in certain super young Mills theories. And I want to start with just a quick overview about what my talk will be about. So we looked at certain super young Mills theories, and an important role in these is played by maximally supersymmetric young Mills theory, so n equals 4 super young Mills theory. And so I will begin with kind of just a short discussion on this theory. And amazingly, despite this theory being a conformal field theory, it has a spectral problem. The anomalous dimensions form kind of a spectrum in this theory. And for certain operators, we can compute these anomalous dimensions. And then we ask the question, given these spectra, what can we learn about the underlying model? And it is known for quite some time that you can find integrability and chaos in spectra. And so I'll kind of discuss a bit chaos and integrability in the context of a spectral spectral statistics. And these two discussions will maybe be a bit independent of each other, but then afterwards, in kind of the main part of the talk, I will try to bring them together, use spectral statistics in super young Mills theories to find integrability and chaos. And I will look at n equals 4 in the planar limit and at the non-planar case, but I will also look at a bigger class of theories, the so-called Lie-Strasser theories, and I will also discuss the transition between integrability and chaos. Okay, so let me start really at the beginning with why it is interesting to study supersymmetric young Mills theories. And there are many reasons to study them, and one important reason is that they are very simplified versions of more physical theories like QCD. So QCD is a four-dimensional young Mills theory with gauge group SU3. And maybe the most simplified version of QCD is n equals 4 super young Mills theory, which is also a four-dimensional young Mills theory, and most people study it with gauge group SUN. And this theory is a simplified version of QCD, in that we have a maximal amount of supersymmetry allowed for a renormalizable quantum field theory, and also the theory is conformal. And this amount of symmetry can help us in answering questions that we cannot answer yet in a more physical theory. For example, in QCD, it would be great if we could compute of spectra of composite particles like hadrons and mesons, maybe even nuclei. But it is too hard for us to deal with analytically with the usual quantum field theory methods. And so one direction you can go to try to advance our methods, or even just our understanding of this problem, is to look at simpler theories like n equals 4 super young Mills theory. And now, this theory is a very unphysical simplification of QCD. Not only is it supersymmetric, it is also a conformal field theory. So in some sense, there's not even like an energy or mass spectrum in this theory. But there is a hidden spectral problem. The conformal field theory, or the conformal group, contains the dilatation operator, which I'll denote by D here. And so the dilatation operator is a symmetry generator in these theories, and it really is just the usual operator rescaling space-time coordinates. And on the space of local operators, which I'll denote here by O of x, so x is the space-time point, the dilatation operator acts like this. So this last part here just describes kind of the action of the dilatation operator on the space-time point x. And then these terms here describe kind of the action on the field content of the operator. And this first term is just the classical scaling dimension corresponding to the mass dimension of the operator, O, and I can kind of just read it off from the Lagrangian. And so this is kind of a rather trivial part, and then the anomalous dimensions are the quantum correction to this classical dimension. And these are really the objects that I will discuss in this talk, and they are part of the non-trivial conformal field theory data. And so in some sense, you can understand the dilatation operator as the Hamiltonian of our problem. These local operators will be kind of our multi-particle states, and the spectrum of anomalous dimensions is kind of the energy spectrum of the theory, and these are the objects that we'll look at. And in n equals 4 super Yang-Mills theory, as we have so much symmetry at hand, we can actually write down the form of this dilatation operator to one loop order in the Yang-Mills coupling of the theory. And so I will discuss this operator in a bit more detail later, but just to kind of say already, we have the dilatation operator, and so we can in certain sectors diagonalize it to obtain anomalous dimension spectra. And actually similarly for certain deformations of this theory of n equals 4 super Yang-Mills theory. And then the question is, given these spectra, can we do something with them to learn more about the underlying theories? And this question of what one can learn from a given spectrum about the underlying model is a very old one. And so I'll just review certain bits that we also used in our work. And for this, I have 3 spectra here. The first one is just the spectrum of the harmonic oscillator, so the energy levels are evenly distributed. And then on the other side is kind of the opposite of the spectrum. Here I pick the energy levels randomly, so the mean level spacing in all of the examples is the same, but here if I pick levels kind of randomly from a certain interval, then they can be quite far, but also arbitrarily close, like here and here, they are levels that are almost on top of each other. And such a spectrum I'll call uncorrelated spectrum or Poisson spectrum, and an example for this are the energies of the Heisenberg spin chain or XXX spin chain, which is an important model in the context of n equals 4 super Yang-Mills theory, so I'll come back to this in a bit. And then I have a third spectrum here in the middle, and you can see that here the levels are not so regular, maybe as in this first case, but they're also not as kind of irregular as in this last case. But they don't want to get too close, and they don't want to get too far. And this spectrum is related to random matrix theory. And in random matrix theory, in this kind of field of study, you can look at many so-called ensembles. And here, this spectrum I generated by diagonalizing a random matrix from the Gaussian orthogonal ensemble, GOE. And this is the ensemble containing the real symmetric random matrices. And this is a very important ensemble for physics. Wigner already in the 50s realized that those GOE spectra resemble the spectra of large nuclei. Not so much in kind of the position of individual energy levels, but in their overall statistics. And this realization then really initiated the whole development of random matrix theory, and people realized that a lot of physical spectra can be described by random matrix theory, in particular the Gaussian orthogonal ensemble. And actually people realized that it is quantum models that have this spectrum that have chaotic classical limits. So they would have been considered quantum chaotic. And so despite chaos being chaotic, there is some structure in these models in that the distribution of energy levels resembles the distribution of eigenvalues of random matrices. And these observations then led to the conjecture by Boygas, Giannoni, and Schmidt that quantum chaotic models have spectra that look like random matrix theory spectra. So kind of in this direction. And then over the years, in lack of a good definition of quantum chaos, this connection, the fact that a spectrum can be described by random matrix theory was actually used as a definition of quantum chaos. So it was kind of turned around. And so I will also kind of use this direction and will use this appearance of random matrix theory in the level statistics of spectra as a definition of chaos. And I'll elaborate more on this during the talk, like what sort of observables you can look at, etc. And similarly, people also realize that quantum systems that are integrable, like the Heisenberg or XXX spin chain, but many more models, they have spectra that are Poisson distributed. And then it was conjectured by Berry and Harbour that, integrable models have spectra that are Poisson distributed. And so in all of these cases, we have different correlations between the energy levels, and these correlations can really tell us about the underlying model. And really the amazing point here is that this is applicable to a wide range of models. So there's some universality in spectra. So if we don't focus on computing individual levels, but really look at their statistical properties, then we can see this universality and learn something really about the nature of the underlying model. And so in our work, we took, if you want, these definitions of chaos and integrability and applied them to the spectra of certain conformal super-Yang-Mills theories with the hope to get a better understanding of universal properties of observables in these theories. Okay, so kind of hopefully having motivated why it could be interesting to look at spectra and super-Yang-Mills theories, I will in the following first talk a bit more about these anomalous dimension spectra and how we obtain them. So I will kind of come back now to n=4 super-Yang-Mills theory, and I already said in this theory we have a lot of symmetry, actually so much symmetry that we can write down the form of this dilatation operator to one loop order in the Yang-Mills coupling. And I will not write down the full formula, but in a particular sector of n=4 super-Yang-Mills theory, it has a rather simple form. And so let me just kind of remind you that n=4 super-Yang-Mills theory contains gluons, which I packaged into a covariant derivative here, and then fermions and scalars. And the scalar SU2 sector is the sector spanned by two complex linear combinations of 4 of the 6 real scalars, which I'll call X and Z. So X and Z, they span the SU2 sector. And now we would be interested in local gauge invariant operators, where I take those X's and Z's and put them into traces, and I can form single trace operators like this here or this. And I can also build multi-trace operators just by taking products of traces. And those multi-trace operators, in some sense, they're the composite kind of objects of this theory. And so if you want the nuclei of n=4 super-Yang-Mills theory. And let me also mention here that we looked at n=4 with gauge group SUN. So this n here is the rank of the gauge group. And now, associated to each of those operators that I can build is an anomalous dimension, and we can obtain these anomalous dimension by diagonalizing the dilatation operator in this sector. And it is given by this relation here. And this first term is just the tree-level dilatation operator that gives you the classical scaling dimension. So it contains the two fields, X and Z, that span the SU2 sector. And then there are also those X checks and Z checks here, which kind of act like functional derivatives on the fields X and Z, and their action is given here. So for example, if I have a trace with a Z check in here, and I want to act with this Z check on a Z in a different trace, then this is how this will act. It's basically just derived from the gauge group. And here those A's and B's are just combinations of X's and Z's, but really here I'm just acting with this Z check on the C here. And similarly, if the Z check acts on a Z in the same trace, then this is the rule. And I mean, the explicit form is maybe not super important, but you can already see that the limit of n going to infinity might be special, and I'll come back to this. So this here is, as I said, the tree-level dilatation operator, and just to give you a very quick understanding of how it acts. So if I take D0 and act on a very, very simple operator, trace Z, this thing won't contribute because the X check will always annihilate the state. It's really only this thing here. And so if you take this Z check and act on one of the Z's, for example, this here, and then use this rule, then you get trace of Z. So this term here won't contribute because I will only have a single Z in each of those traces. And since we're in SUM, this vanishes. So this is the action of this thing here on one of the Z's, and the other Z I get the same. So this is just two trace Z. So in some sense, this counts the number of Z's I have in an operator, and similarly, this counts the number of X's in an operator. And so in total, I'll just get the length of an operator in the SU2 sector from this operator. And this is just the classical scaling dimension for a scalar operator in 4 dimensions. Then the next term is the one-loop contribution, which I'll call D2. And this lambda here is just the gauge coupling G squared times the rank of the gauge group. And this operator now contains products of 2 of those functional derivatives. And so this operator can really change the structure of the operator I act on. If I just take this and act on trace Z, then this will annihilate the state. This X check will always kill the state. But if I look at an operator that's a bit more complicated, this double trace operator here, then what you can see is that this double trace operator gets mixed into 2 single trace operators. And so when looking at how the one-loop dilatation operator acts on a general local operator, you find that the multi-trace operators mix. And so the SU2 sector is closed. So like you will never, if you only start with X's and Z's, well, you will never find any other fields, but there's kind of a non-trivial mixing here that you have to diagonalize to find the spectrum of anomalous dimension. And so now you, if you, for example, wanted to solve this mixing problem, then you think about which operators could possibly mix, and then probably come up with this list, and then you take the dilatation operator, act on these operators to find the mixing matrix, and then you can just diagonalize it. And if you do this, then you find that there are 3 eigenoperators with vanishing anomalous dimensions. They are protected, and then there's one operator that gets a non-vanishing anomalous dimension of 12 lambda. So this is kind of how you can solve the mixing problem for other short lengths. And what really made people study this theory extensively was and is the hope to do better than this, to obtain analytic expressions for the scaling dimension, which do not involve this diagonalization of such a mixing matrix, but really a compact analytic formula. And in a certain limit of the theory, the planar limit, this is actually a key. In this limit, the rank of the gauge group is set to infinity. And the dilatation operator there essentially becomes the Hamiltonian of the Heisenberg spin chain. So it only acts on neighboring X's and Z's in a trace, and up to a prefactor, it's a sum over the action over all of those neighboring X's and Z's, and then the action is just the identity operator minus the permutation operator. And this is the Hamiltonian of the Heisenberg or XXX spin chain. And then as mapping single trace operators get mapped to cyclic spin chains. And this Hamiltonian is integrable, which roughly speaking means that there are as many symmetries as there are degrees of freedom. And so in theory, can kind of compute anything we want. And so in this planar limit, the symmetry structure of n equals 4 Spiering node theories is kind of further enhanced, and the theory becomes integrable. And yeah, integrability is a powerful tool. It gives us techniques to essentially solve the planar spectral problem at weak coupling with a beta ansatz, but also at strong coupling. And there's even a non-perturbative description for the planar anomalous dimensions. So the planar spectral problem is essentially solved. At finite n, we do not know how to diagonalize the dilatation operator in the general case. And this is really important. Physical theories do not have an infinite rank of the gauge group. In physical theories, this number is finite. In particular, in QCD, it is 3. And here, the theory is not supposed to be integrable, and we do not have a general analytic approach to the spectrum. Yeah, there are some approaches to non-planar correlation functions, but it's not as advanced as in the planar limit. But we can, like also at finite n, we can compute anomalous dimensions by direct diagonalization of the dilatation operator, and we do this for kind of a large number of short operators, and so we obtain kind of large sets of anomalous dimensions, and then try to understand universal features of these spectrum. So in practice, you kind of take this dilatation operator here and implement it, for example, into Mathematica, and then you can pick your favorite operators, act with the dilatation operator to find the mixing matrix, diagonalize it to find the anomalous dimensions. And before you can do the analysis, you have to do a tiny bit of data preparation, but I don't really have time to discuss it. But we can discuss it after the talk if you're interested in. But then once you've computed the spectrum and cleaned up a bit, then one of the standard observables is the nearest neighbor spacing distribution. So for this, assume these are some of the levels that are obtained, and then I would compute the nearest neighbor spacings. I'll denote them by little s, s1, s2, s3, and so on. And then I would take those spacings and then kind of bin them, compute the ratios of the ratio of spacings lying in each bin to get the probability distribution. And before kind of coming to our results, let me quickly discuss what could be the result of such an analysis. So if I take this uniform spectrum, the levels are separated by the same amount, and so I get the Dirac delta function here. For the uncorrelated or Poisson spectrum, I get the Poisson distribution, which is this bluish curve. And then for random matrix theory, depending on the ensemble, I get different distributions. And here I have the results for the Gaussian symplectic, unitary, and orthogonal ensemble. This Gaussian orthogonal ensemble is the one that I mentioned earlier here. The distribution is this yellowish curve that was approximated already by Wigner as roughly s times e to the minus s squared up to integers and factors of pi. And so this is the ensemble of quadratic matrices that are invariant under orthogonal transformations. And then there's the Gaussian unitary ensemble, so the ensemble of matrices invariant under unitary transformation. And then we have the Gaussian symplectic ensemble, the ensemble invariant under symplectic transformation. And so conjecturally, this Poisson behavior, this blue curve, appears for integrable systems, and all those random matrix theory ensembles relate to different versions of quantum chaos. Okay, so now let me come to some of our results. So here are the results for kind of the spacing distribution of the spectrum of length 16 operators. So I have 16 x's and z's in my traces, and actually there are 7 x's and 9 z's. And so this is those red points are the data from the kind of this spectrum in the planar limit. And you can see that up to to a bit of statistical fluctuation, the data points follow the Poisson behavior quite nicely. At finite n with operators of the same length, you find a different behavior. Here the data points follow the expected distribution for a random matrix theory ensemble, this Gaussian orthogonal ensemble. And so from this we see that, well, in the planar limit, the spectral statistics manifest the quantum integrability of the theory, whereas at finite n, the theory is not integrable, but rather we find that the spacing distribution can be described by a random matrix theory, and so the theory is quantum chaotic. And actually I have to admit that I cheated a bit in these plots, because these data are actually not from pure n equals 4 superannular theory. I could have actually also shown you the results for the antiform theory, just the statistics aren't great, in particular in the planar limit, where the mixing of the single trace operators decouples from the multi-trace operators. The sectors that you can analyze are very small, and so you need to go to high operator lengths, which gets computationally more and more expensive. So instead, I show you here the data of a very similar theory, a slightly deformed version of n equals 4 Spiering-Wells theory called beta deformed n equals 4. And this theory is kind of just as integrable as n equals 4 in the planar limit, and similarly at finite n, it is not integrable. And yeah, we find that in both those theories, the non-planar spectrum can be described by random matrix theory. And this is actually a good transition to the next section, which is about generalizing the discussion to more general Spiering-Wells theories. So yeah, this previous discussion was for very specific models, pure n equals 4 and beta deformed n equals 4, which are both known to be integrable in the planar limit. And with the spectral statistics analysis, we find that they are quantum chaotic at finite n. But yeah, these models are very specific. To kind of broaden our understanding, we extended these analyses to a wider set of Spiering-Wells theories, which are again conformal deformations of n equals 4 Spiering-Wells theory. And these were already classified quite some time ago and go under the name of Lie-Strasser theories. And these are all the conformal supersymmetric four-dimensional theories that you can reach from n equals 4 Spiering-Wells theory by exactly marginal deformations. And this new set of theories has a priori 3 parameters, lambda prime, q, and h. Although there is an additional constraint which fixes one of these parameters, usually you take lambda prime, to be a function. So this lambda prime is actually a function of q and h, so that the theory is actually conformal. And yeah, you can obtain this theory by deforming the n equals 4 superpotential to be of this form. And then in the planar limit, now I'm actually going to the SU3 sector, which is spanned by 3 scalars, which I'll call phi1, phi2, and phi3. You can again compute the planar dilatation operator. And what you find, or what the authors of this paper here found, is this expression here. So the planar dilatation operator also of these Lie-Strasser theories is again in nearest neighbor Hamiltonian. So here the superscripts denote the action of kind of the action of the operator on what fields in a single trace. And then this Hamiltonian density is given here. And so, for example, here this first term contains an E1, 1. So the subscripts, they denote the flavor action. So this thing here contains an E1, 1, and this is just the operator mapping a field phi1 to another field phi1. Here there's one of the terms is an E2, 1. And this is just the operator mapping a phi1 to a phi2. And so we have kind of all these different terms with different prefactors depending on q and h. And now if I send h to 0, then all those terms drop out. And if I also send q to 1, then you can combine this and this operator to the identity operator, and you can combine this operator and this operator to the permutation operator, and then you just find the identity minus the permutation operator, which is just the Heisenberg Hamiltonian. So so Q being 1 and H being 0 corresponds to the undeformed theory. So N equals 4 Spiering Mills theory. Kind of more generally, these super Yang-Mills theories in the planar limit are still conformal and have N equals 1 supersymmetry, but they don't necessarily need to be integrable. In fact, it seems like there are only certain subclasses of theories that are integrable. And this was also analyzed by Watson, and they found this list of integrable points. So, so of course it contains N equals 4 Spiering Mills theory, where H is 0 and Q is just 1. And but you can also just have Q being a phase, and that's integrable in the planar limit, which is just a beta deformed version. But yeah, there are other integrable points that are known. Okay, and now so we kind of also took this Hamiltonian and then studied spectra of this these planar super Yang-Mills theories, and at these integrable points, what we find is that again the level statistics are follow the Poisson distribution nicely. So this is all consistent with the expectations. So for integrable points, we have the Poisson distribution, the spectra are uncorrelated. And then what happens as we go away from these integrable points, the expectation is that the distribution shouldn't follow this Poisson behavior anymore. And indeed, if I use a certain sector of length 11 states, with a planar dilatation operator with these values for Q and H, which do not correspond to any of the integrable points I showed you earlier, we find that the spacings are not uncorrelated anymore, but instead are best described by random matrix theory, and this points towards chaos. And specifically, we find that at generic values of Q and H, the spectrum can be described by the Gaussian unitary ensemble. And maybe if you remember before in the case of the non-planar chaos, we found the Gaussian orthogonal ensemble, and here we find the Gaussian unitary ensemble. And what ensemble exactly you find relates to certain symmetry properties of the models. And in particular for the Gaussian orthogonal ensemble, you need some sort of symmetry that provides a reality condition, so that in a specific basis, the Hamiltonian or the planar dilatation operator can be made real. And so you can show that there are these discrete symmetries in the non-planar model, which make the kind of the spectrum GOE. And whereas in this model here, this construction does not exist. These symmetries do not exist. And so we find the Gaussian unitary ensemble, which is kind of the most generic of the Gaussian ensembles. So yeah, at integral points, we find the Poisson distribution. At generic values, you find this Gaussian unitary ensemble. The case of vanishing H is particularly interesting because for this model, we can construct the gravity dual. And so we can investigate a given theory kind of with certain values of beta and kappa that I define here. So beta and kappa are both real. And so we can kind of investigate a given theory with certain values of beta and kappa on both sides of the CFT of the ADS CFT duality. And in particular on the gravity, so string theory side, string trajectories were studied, and for the case of Q being real, so beta being 0, it was found that the equations of motion governing the trajectories of strings correspond to non-integrable Hamiltonians, and also the phase space trajectories were found to be strongly sensitive to the initial conditions. And so the authors of this paper here find classical chaos in the dual string theory. And so we wondered whether we can kind of find the quantum analog of this by studying the corresponding weak coupling gauge theory and the level statistics there. And indeed, for beta being 0, or like in the kind of more general case, for beta and kappa, we find these plots here. For beta being 0 and only kappa turned on, the result are those yellow dots, which follow the Gaussian orthogonal ensemble prediction. I also plot here the results for kappa being 0. Here the theory is just the usual beta deformed n equals 4, which is integrable, and you can see the blue data points again follow the Poisson curve. And when I turn on both beta and kappa, then the distribution corresponds to the Gaussian unitary ensemble. But yeah, for beta being 0 and kappa turned on, the distribution is described by the Gaussian orthogonal ensemble. And so in this sense, we find the recoupling chaos as the quantum chaos defined by the level spacing statistics being described by a random matrix theory. And then we actually also looked at this gauge theory in the so-called Landau-Lifshitz limit, which is a limit of infinitely long operators with low energies. And in this model, in this limit, the model has a semi-classical description in terms of a two-dimensional Landau-Lifshitz type sigma model. And actually the same model can be found from taking the appropriate limit in the dual string theory. So this is one of the tests of the ADF-CFT correspondence in these cases. And we studied the dynamics of this Landau-Lifshitz theory related to those Lie-Strasser deformations, and show that for specific solutions, the dynamics is classically chaotic. So we numerically find the Lyapunov exponents, and they are non-zero. So we find that the model is classically chaotic. So we kind of, from this recoupling point of view, we find kind of the quantum chaos from the level statistics analysis, and then also by studying the Landau-Lifshitz limit, we find classical chaos in these models. I won't discuss the second point further here, but if you want more details on this, we can discuss it later. I also have a backup slide for this if you want to see some plots for this. Okay, but then I would move on to the transition between integrable and chaotic statistics. So far, I've always shown you plots for kind of extremal cases. The statistics were either uncorrelated, Poissonian, or correlated and described by random matrix theory. But in all these cases, there was kind of a parameter that was tuned to obtain these results. For example, in the case of the planar versus non-planar statistics, there's this parameter n, the rank of the gauge group, that you can kind of tune to be infinite or very large and to be finite. And so you might wonder how the transition between the two extremal cases behaves. And in these plots, I show you the statistics, how the statistics transitioned from the chaotic distribution at small n to kind of the Poisson distribution at infinite or large n. And this is for length 15 operators in the beta deformed theory, where we have kind of combined the distributions from various impurity sectors to allow for better statistics. And you can see that actually you don't really have to go to very high n to find this Poisson statistics, although really the crucial part here is for small spacings, where even if you go to very high n but not infinite n, the levels repel, which you can see in this very first dot. So even kind of in this case, the distribution will go down for small s, and only if you go to n being infinity will it go up to 1. Now, it would be nice to find kind of an analytic expression that interpolates between the integrable and chaotic distributions, but and for this, we would need analytic control over the spacing distribution, which has only been achieved in a handful of rather simple models. And so oftentimes people instead approximate the transition using the so-called Brody distribution. And for this, I have a short slide here. And this Brody distribution is this function here. It is a function of the spacings f. And it also depends on omega, on the parameter omega, which interpolates between the Poisson distribution for omega being 0 and the random matrix theory distribution for the Gaussian orthogonal ensemble at omega being 1. And here I plot this distribution for a few values of omega between 0 and 1, where you can see quite nicely how it does this interpolation. And so now we can kind of compute the level statistics for intermediate ranges of the deformation parameter, so the parameter that interpolates between the integrable and chaotic statistics, and then one can approximate the distribution by this Brody distribution and extract the best fit value for this omega. And so in our work, we studied the transition between planar integrability and planar chaos in these Lee-Strasser theories. And yeah, the study of this transition is motivated by the rather recent observation from this paper here, that there are different types of integrability breaking deformations. There's strong integrability breaking, which is kind of the generic case. And then there's also weak integrability breaking, where the onset of the chaotic dynamics is slower as you turn on the deformation parameter. Actually, the term weak integrability breaking has been used for quite some time, but it used to refer to adding a deformation, but keeping the parameter determining the strength of the deformation small. And here, kind of in this paper, the terms strong and weak are related to different types of deformation. And so a deformation can be weak even though you turn it on a lot. And yeah, these terms strong and weak are intimately connected with symmetry breaking by the deformation. The idea being that integrable models have kind of a tower of conserved charges, and strong integrability breaking is related to breaking all of these symmetries, whereas weak integrability breaking is connected to the idea of only breaking most of the charges, but some symmetries might persist. And so the onset of chaos in the second case is slower. And now, to kind of measure the strength of integrability breaking, you could compare the crossover between chaos and integrability for different deformations. And then you call the ones where the onset is slow or weak, and the ones where the onset is quick or strong. But yeah, then you can only really compare between two models, and you have to be careful with normalizing the deformation parameters and making the deformations really comparable. Actually, the idea of these terms strong and weak is more about the question of whether a given deformation generically breaks the integrability in the strongest sense possible. All symmetry charges are broken, or whether the integrability breaking is weaker. Maybe the charges are not all broken. And so in this sense, it would be nice to have an absolute measure for the integrability breaking that one can extract from the spectrum kind of, and you can kind of compute for each deformation independently without comparing it to other deformations. And for this, the authors of this paper identified the volume dependence of the crossover between integrability and chaos. And I'll discuss this more on the next slide. And but just to kind of be complete, so the authors of this paper study these terms for the XXZ spin chain models, and we were interested in understanding the strong and weak integrability breaking in the context of the deformations that we looked at. And in particular, we looked at the planar Lee-Strasser theories, and the case I already discussed earlier where H is 0 and Q is turned on. There, you could also look at kind of both Q and H being turned on, but there are certain complications when really looking at this transition. We can discuss this later, but this is kind of a good setup to test this transition between chaos and integrability. And so I'm looking at this, and kappa here is really kind of this parameter that can be tuned. For kappa being 0, the model is integrable. It's just the beta deformed case. And if you turn on kappa, the model becomes chaotic. And so we study this transition. And so we kind of compute the level spacing distribution for various values of kappa, and then fit the data to the Brody distribution. And we do this for various lengths of the spin chains, or like various numbers of field insertions into the trace. So for the blue dots, I have 13 field insertions, and this kind of goes all the way up to 17. And so we compute the spectrum and the spacing distribution for various lengths and various values of kappa, and then we compute omega, this parameter in the Brody distribution, which for omega being 0 indicates integrability and omega being 1 chaos. And so you can see that for kappa being 0, the best fit is omega being 0, where the Brody distribution corresponds to the Poisson distribution, which signals integrability. And then as we turn on kappa, the value for omega grows and approaches 1, where the Brody distribution corresponds to the Wigner-Dyson distribution for random matrix theory. And you can already quite clearly see that although the general trend is the same for different system sizes, so different lengths of the operators, there are quantitative differences in the growth of omega as a function of this L. So for larger L, the system transitions over to the chaotic case more quickly, like here for L being 17, it kind of transitions to 1 much quicker than in this L being 13 case. And this is actually a known universal behavior for the transition between integrable to chaotic statistics. And to quantify this transition, we define a crossover coupling kappa C between integrable and chaotic statistics, and it's the value of kappa for which omega is 0.5, so kind of just in between the integrable and chaotic case. And then we study the volume dependence, or the L dependence of this crossover coupling. And if I extract the these values here from this plot, then you get those data points here. And it was already observed that there is in some sense, like a universality in this crossover. In particular, it was conjectured to scale with the volume as some power law, and that actually the explicit value of this exponent does not depend on the microscopic details of the deformation, and indeed it is conjectured to be 3. In the most generic case, which was done in these papers here. And so we went ahead and tried to fit our data to such a power law. And what we find is that indeed the best fit is alpha being 3. And so this result is consistent with strong integrability breaking of the Lie-Strasser deformation. Okay, so now before closing this, I just have another slide, and here I just want to summarize a bit another model that we looked at in our research paper. If you want like a deformation of this 1 loop n = 4 dilatation operator, and this deformation is the known 2 loop piece. So as I said, n = 4 for n = 4 Spiering theory, we know the full 1 loop dilatation operator in the SO2 sector, it is this. But to 2 loop order, we actually, we don't know the full dilatation operator, so kind of in the whole n = 4 sector, but we do know it in the SO2 sector. Here I just write the first term, but kind of this full thing here is known, and you can find it in this paper here. And so in the planar limit, this operator here, as we talked about before, this becomes the integrable Heisenberg Hamiltonian, and then conjecturally the full planar theory is integrable. So at any value of lambda. So conjecturally this full thing is an integrable Hamiltonian. But now imagine I take this expression and then truncate it after the 2 loop piece. Then kind of this dilatation operator, even in the planar limit, cannot be expected to be integrable anymore at finite values of lambda. It is only like integrable perturbatively when adding higher loop terms. And so we wondered what actually happens when we study this model. with this level statistics analysis. And so, yeah, in some sense, deforming this planar, well, in the planar limit, integrable system by a term corresponding to the two-loop planar dilatation operator. And again, I have a few plots. The first one is just the undeformed planar case. So we find integrability, the spectrum is Poissonian. And then we add the planar two-loop dilatation operator and kind of turn on the coupling and turn it on to a finite value. And then we find these level statistics here. So again, in the planar limit, the whole theory is supposed to be integrable, but when we chop off higher loop pieces and look at the spectrum, the result is that the spectrum is compatible with random matrix theory, the Gaussian orthogonal ensemble. So we find that the theory becomes chaotic. But actually, if you study the transition between the integrable case and the chaotic case, we find that this deformation is only weakly integrability breaking. In particular, in the beta deform case, the scaling of the crossover coupling is roughly L to the -1. So the two-loop term deforms the model to become chaotic, but it is nonetheless non-generic and only gives rise to a weakly chaotic system in the sense that the transition between the integrable and chaotic regimes is slower than in the most generic case. And this analysis is actually a very similar analysis to the one from this paper here, where the authors look kind of at the XXZ spin chain, and they find a similar weak integrability breaking for deformations that can be constructed by a so-called boost method. And you can kind of similarly construct the planar two-loop dilatation operator here by this boost method. So this result is kind of consistent with our current understanding of weak and strong integrability breaking terms, in the sense that weak integrability appears for models where a higher loop completion to an integrable system exists. Okay, so this brings me to the end of the talk, and I'll just quickly finish with a short summary and a few words regarding possible future directions of work. So I started with a discussion of n equals first Spiering-Mills theory at the planar level and at finite n. And what we find is that the statistics of the planar spectra are compatible with the planar integrability of the corresponding model. And then I started to deform this planar integral model, and what we find is chaos. The first deformation I looked at was this non-planar deformation, and here, both for the undeformed and the beta deformed theory, you find that the spectra are well described by random matrix theory, making them quantum chaotic, and so we conjecture that n equals 4 and its beta deformed version are chaotic at finite n. But there is still structure. The statistics of eigenvalues can be described by the Gaussian orthogonal ensemble. And then as a second deformation, we also looked at Lie-Strasser's spin chain model, so planar limits of certain Spiering-Mills theories, and we found that in the most generic case, the resulting model is quantum chaotic. The spectra are well described by random matrix theory, in particular this Gaussian Unitary ensemble. Though there are also integrable points, and there we see Poisson statistics, and in this discussion we also found the weak coupling analog of classical chaos found in the holographic string dual. And here we actually also studied the transition between integrable and chaotic statistics, and from these analyses we find that the Lie-Strasser deformations lead to strong integrability breaking, which is kind of expected. So far, weak integrability breaking has only been observed, as I said, from models with an integrable higher loop completion, which is not known for these like Lie-Strasser spin chains. And then I also discussed a bit at the end a third deformation of this planar one loop case where we add a finite two loop piece. This breaks the integrability, but the resulting model is only weakly chaotic. So it transitions to chaotic dynamics more slowly than in the generic case, which is consistent with the idea that some of the integrability structure survives and indeed can be completed at higher loop orders to an integrable theory. And yeah, let me just finish with a few words on open questions or possible future direction. And so I think kind of this method of using statistics on numerical spectra is an interesting way to learn something about a model, especially when it is not accessible by analytic means. This is really a general approach, and so using it in other contexts of high energy physics would be interesting. This is, of course, already underway. In particular, like, for example, the SYK model has obtained much attention. And then when continuing further with this analysis now of n=4 Spiering-Mills theory, trying to see whether one can learn more from the spectrum. So we looked at the level spacing distribution, which is kind of a short range observable, with which you can really only say whether something is Poissonian or one of those random matrix theory ensembles, but not much more. Something a bit more fine-grained where we can extract more information would be interesting. In the paper, we actually did also look at more like long-range correlations and at the statistics of eigenvectors. But exploring this further would be interesting. For example, the chaos in all these deformations that I looked at from the point of the level spacing distribution kind of looks the same. And so we looked at this transition between chaos and integrability to learn more about the chaos in these different cases, and could see that actually the chaos from the two-loop truncation is of a different type than the chaos in the Strassler deformations. But I think this is more potential, trying to find new probes to see further differences in kind of the physics of this chaos would be interesting. And then also the question of looking at other data of the theory, for example, the structure constants or scattering amplitudes would be interesting. And these are kind of the points I wrote down, but really the overall question would be to better understand universal properties of some Spiering-Mills theories, in particular when going away from the now well-studied maximal supersymmetric case. Like, we seem to lose integrability, but there is still some structure. The distribution of scaling dimensions is described by random matrix theory, which is a property of chaos, and exploring this chaos further will hopefully provide deeper insights into these theories. But yeah, with this, I'll finish. Thank you.
Thanks a lot, Hen, for the great seminar. I think now we can open for questions. Okay, there is a question.
Okay, hello. Thanks for the nice talk. Wondering if one can use this mapping of single trace correlators to the spectrum of spin chains to learn about black holes in the book, like black holes in the S5, to try to understand some properties of maximal quantum chaos, for example, which happens in the GGT gravity and random matrix theory dualities and such things.
So in the context of n=4 Spiering-Mills theory,
like finite temperature or something on the Spiering-Mills side.
Yeah, this, I mean, in some sense was kind of our motivation. People are studying chaos in the string theories and then trying to understand what it means in the dual gauge theories. But yeah, going to strong coupling is really hard from this kind of weak coupling point of view. And so one thing you can do is this Landau-Lifshitz limit, which kind of works from both sides of the duality. And so we try to approach gravity kind of slowly by looking at this Landau-Lifshitz model. It would be really great to connect more with the gravity side, but at the moment I'm not quite sure how to do this.
Okay, thanks.
Okay, I have a question. First of all, I want to thank. It was very clear and interesting talk. And my question is about, first question is about understanding. So in the beginning, you discussed the difference between integrability and chaotic systems, and you said that integrable models, they're characterized by universality, and the chaotic models, they're characterized by classes of random matrices, right? So there's also some universality in the sense of these classes of random matrices. So is there any difference between these universalities, or is there universality in the same sense for the chaotic systems?
Yeah, this universality in some sense is supposed to be the same. Like integrable models have spectra that are described by Poisson statistics across all sorts of models, like spin chains, but other models also for the chaotic case. I mean, there are always like certain exceptions to this. Like there are, I'm not sure which direction it goes. I think there are chaotic models. If you have like or maybe integral. Sorry, I'm not quite sure which way around, but I think you have integral models where there's like a parameter that lets you jump from one integral model to the other. And if you fine tune this parameter, then you can actually find kind of chaos in the spectrum. So the spectrum is described by random matrix theory. But as soon as you go away from this very fine-tuned parameter, you recover the Poisson statistics again. So it's universal up to with a little asterisk. So, yeah. Sorry, is this an answer to your question?
Yeah. Okay. So it is not universality in the sense of critical exponents and classes like that, or it's a different kind of universality you're talking about.
It's a universality in kind of the statistics of the spectrum, or actually the fluctuations around the overall trend of the spectrum. And I mean, you can try to connect with this classical notion of chaos, those Lyapunov characteristic exponents. But there is some work on this, but for general theories, it's not well understood how those two concepts, classical chaos and quantum chaos, connect.
Right. So this Brody distribution, is it just an approximation, or there is some model where this Brody distribution is exact, for example?
From what I know, it's really just an approximation. There are other approximations. One which was computed by Barry, I think, and this approximation really comes from certain models which have a semi-classical limit, and there you could really kind of connect in those models he looked at. You could connect quantum chaos and classical integrability. Quantum chaos and classical chaos. But as far as I know, the Brody we can this analytical approach to quantum chaos has only been achieved really in a handful of models, and so I think the Brody distribution really is kind of just an approximation. An approximation.
Yeah, the reason I was asking, I thought maybe you can do some reverse engineering and trying to understand something about systems and strong coupling, but I guess it's a wishful thinking. So my final question is about, you mentioned that you need to do some preparation of the data. Maybe you can comment something about this.
Yeah, I think I also have some slides on this. And one important thing is unfolding that I maybe mentioned a bit before. So if you take just kind of a mathematical construct a random matrix and then diagonalize it and plot the spectral density, and what you find is Wigner's semicircle law. So at the edges of the spectrum, you only have a few states, and really most of the states are in the bulk of the spectrum. But this is not a physical spectrum. Like for example, in the Spiering theories that we looked at in the planar limit, we kind of this sector here, we find this form of the spectral density, and in the non-planar case, you find this. And also, if you look at heavy nuclei, this is not physical. And really, this idea of looking at the spectral statistics is more about fluctuations around this average trend, and to kind of concentrate, to kind of remove the average trend and really only look at the fluctuations, you have to do a procedure that is called unfolding, and there are like formulas for these. Maybe it's so you kind of have to separate the average trend and the fluctuations, and then there are there are methods for doing this unfolding. And so this is one thing. And another thing is that you have to be very careful with symmetries in the model. For example, for the Heisenberg spin chain, there's a parity, but there's also, well, in the planar limit, single trace, the mixing of single trace operators decouples from the mixing of multi-trace operators. And if you left those symmetries in the spectrum, then they would always look uncorrelated. They would always look like the Poisson case, and sometimes even like with a peak at 0 for all the degeneracies in the spectrum. And to really kind of look beyond all those symmetries that we can kind of see from the Hamiltonian, you have to desymmetrize and really only go to sectors of specific quantum numbers under these symmetries that you have. So, for example, we only look at operators of a certain length. We do not put together the spectrum of operators with different lengths. And we also desymmetrize in the sense that we focus on positive parity states if parity is a symmetry in those things. And then there's also a third thing where if you kind of have the whole spectrum, then towards the ends of the spectrum, even in the chaotic case, the states kind of at the end of the spectrum are less chaotic than in the middle of the spectrum. And so usually one also removes some of the states at the edges, because even if it's chaotic, they are usually more regular because they are more like symmetries constraints of the model. These are all the things I remember now. I think that's it.
Yeah, I think the plots look great. So I guess I don't know how many points were removed, but they look great. Well, thank you. So thank you for the talk.
Thank you for the questions.
I have one question. It's about the analytics. Also, it's following the question by Dimitri. If you take n equals 4, Spiering and look again to this broad distribution, is it which approximate? Is it super good the fit with this? I'm a bit confused about this broad distribution. What assumptions do you have to derive it, and also about if you have some ideas on how possibly compute these corrections analytically in terms of scalar products of spin chains and things like that.
Well, I'm not sure I have any ideas on how to compute this. It's really, it's kind of really hard because not only do I have to have like analytical control over the spectrum, you also have to kind of then do all those things like unfolding. So you need to know what the average behavior of the spectrum is, which once you have analytical control over the spectrum, I guess you can obtain it, but you need analytical control over the spectrum if you want to do it exactly. So I'm not sure how to approach this question. But for the Brody, I think it's I don't have like plots here, but if you kind of look at the spectrum, the level spacing distribution at the intermediate stages, the Brody distribution looks like it's a good fit. But I mean, analytical control would be great, and doing this more analytically, then that would be great. But this is all we did, certainly. Yeah, it's not a very satisfactory answer, but yeah, I'm not sure how to do better.
Okay, thanks. So I'm not seeing any other questions, so let's thank.
Thank you.
So, thank you very much. Thank you very much, Annie. Thank you, everybody.
Thank you. Thanks for the invitation.
And okay.
Bye-bye.